Hello everyone, I am Deeptangshu Banik from ECA section, and today I am going to present my concept video of the subject Linear Algebra and Calculus on the topic Complex Fourier Series. First, let us know what are the contents of this concept video. First, we have what is a Fourier series, then the applications of Fourier series such as spectrum analysis, digital signal processing, analytical applications. Then we will discuss complex Fourier series and will come on to my conclusion. So to begin with, let us discuss what is a Fourier series. A Fourier series is an expansion of a periodic function f of x in terms of an infinite sum of sines and cosines. Fourier series make use of orthogonality relationships of the sine and cosine functions. The computation and study of Fourier series is known as harmonic analysis and is extremely useful as a way to break up an arbitrary periodic function into a set of simple terms that can be plugged in, solved individually, and then recombined to obtain the solution to the original problem or an approximation to it to whatever accuracy is desired or practical. Examples of such approximations to common functions using Fourier series are illustrated in the next slide. Here we have the graphs of square wave, sawtooth wave, triangle wave, and semicircle waves. These all can be converted into Fourier series of sine and cosine functions. The Fourier series of a function f of x is given by f of x is equal to a0 plus summation from n is equal to 1 to infinity of an cos nx plus bn sin nx, where a0 is equal to 1 by pi into integration from minus pi to pi of f of x dx, an is equal to 1 by pi into integration from minus pi to pi of f of x into cos nx dx, and b of n is equal to 1 by pi into integration from minus pi to pi of f of x sin nx dx. The values of a0, an, and bn are known as Euler's formulae. Now, let us know about the various applications of Fourier series. The first application of Fourier series that we have is spectrum analysis. An important instrument to any experimentalist is the spectrum analyzer. This instrument reads a signal, usually voltage, and provides the operator with the Fourier coefficients which correspond to each of the sine and cosine terms of the Fourier expansion of the signal. Suppose an instrument takes a time domain signal, such as the amplitude of the output voltage of an instrument. The next application of Fourier series is digital signal processing. We have already seen how the Fourier series allows experimentalists to identify sources of noise. It may also be used to eliminate sources of noise by introducing the idea of the inverse fast Fourier transform, also known as IFFT. In general, the goal of an inverse Fourier transform is to take the an, the ones that appear in equation 5, and use them to reconstruct the original function f of t. Analytical applications. The Fourier series also has many applications in mathematical analysis. Since it is a sum of multiple sines and cosines, it is easily differentiated and integrated, which often simplifies analysis of functions such as saw waves, which are common signals in experimentation. Some analytical applications of Fourier series are discontinuous functions, convolutions, and generalized Fourier series. Now, let us see what a complex Fourier series is. Let the function f of x be defined on the interval minus pi to pi, with both minus pi and pi being included. Using the well-known Euler's formula, we can say cos of psi is equal to e to the power I into psi plus e to the power minus I into psi whole divided by 2, and sin psi is equal to e to the power I into psi minus e to the power minus I into psi whole divided by 2i. We can write the Fourier series of the function in complex form as f of x is equal to a0 by 2 plus summation from n is equal to 1 to infinity of an cos nx plus bn sin nx is equal to a0 by 2 plus summation from n is equal to 1 to infinity into an into e to the power inx plus e to the power minus inx whole divided by 2 plus bn into e to the power inx minus e to the power minus inx whole divided by 2i, which is equal to a0 by 2 plus summation from n is equal to 1 to infinity of an minus ibn divided by 2 into e to the power inx plus summation from n is equal to 1 to infinity of an plus ibn divided by 2 into e to the power minus inx, which is equal to n is equal to which is equal to summation from n is equal to minus infinity to infinity of cn into e to the power minus inx. Here we have used the following notations. C0 is equal to A0 by 2. Cn is equal to An minus Ibn by 2. And C minus n is equal to An plus Ibn whole divided by 2. The coefficients Cn are called complex Fourier coefficients. They are defined by the formulae Cn is equal to 1 by 2 pi into integration from minus pi to pi of f of x into e to the power minus inx dx, where n is equal to 0, plus minus 1, plus minus 2, and so on. If necessary to expand a function f of x of period 2l, we can use the following expressions. F of x is equal to summation from n is equal to minus infinity to infinity of cn into e to the power I n pi x divided by L, where Cn is equal to 1 by 2L into integration from minus L to L of f of x into e to the power I n pi x divided by L dx. Here n is equal to 0, plus minus 1, plus minus 2, and so on. The complex form of Fourier series is algebraically simpler and more symmetric. Therefore, it is often used in physics and other sciences. Now let's hear my conclusion. A Fourier series is an expansion of a periodic function into a sum of trigonometric functions. It has numerous applications in fields such as spectrum analysis and digital signal processing. It also has its analytical applications. The complex form of a Fourier series is algebraically simpler and more symmetric. Thus, it has many applications in physics and other sciences. I would like to conclude by saying thank you.